Good morning, Miss. In this video, we are going to share the application of differentiation and integration in the engineering industry. These are my group members. They will be explaining in detail of the application.
Before I discuss what is differentiation, what are derivatives? It is represent the rate at which a function changes as its input changes. Mathematically, we define the derivative of a function fx with respect to fs to this formula below. This formula essentially calculates the slope of a function at a specific point. The derivative f prime of x tells us how steep the graph is at any given point. So what is differentiation? It is the process or operation of finding derivative. This involves determining the rate of change of a function and allow us to analyze the behavior of that function at different points. Now let's see about the rules of differentiation, and I will explain one of the allocation of the rules. First, we have derivative of a constant. It can be used to understand the situation where an object is moving with a constant velocity or acceleration. Then we have power rules. It can be used to calculate the reaction rate, especially when the rate law is a power function of concentration. Next, we have constant multiple rules. It is useful when analyzing the time complexity of algorithm. Next, we have quantum rules. It is often used to differentiate functions that describe the relation of two physical quantities. Next is the sum and difference rules. It can be used to analyze the net force acting on a system. Next, we have product rules. It can be used to calculating work done by force and that varies with position of time. After that, we have higher derivative. Higher derivatives are used to analyze vibration in structure and mechanical systems. Last, we have the change rule. It can be used to in algorithms like gradient descent. Now I will discuss the integration. Integration is defined as the process of finding the antiderivative of a function. F of s is the antiderivative of f on a certain interval when it is equal fs of all s in the interval. Integration have a specific symbol which is called integral sign. This represents the operation of integration. The function fs inside the integral is called the integrand. The result of the integration capital F of s is the antiderivative of lowercase f of s, which is the given function. C is the constant of integration because when we differentiate a constant, it becomes zero, and we include it to account of all possible antiderivatives. Let's see the rules of integration, and I will explain one of the application of the rules. First, we have power rules of integration. It can be used to integrate basic polynomials and simple algebraic functions. Then we have subsection rules of integration. It can allow us to simplify this integrand into more manageable parts. Then we have integration as inverse process of differentiation. It can help us finding original function if we know the rate of a change of a quantities. Then we have addition rules of integration. It can allow us to find work or energy when multiplied force or energy component are inverted. Next is constant multiple rules of integration. When constants appear in multiple terms of function, the rule allows us to integrate terms by terms. Next is indefinite integration. It is used extensively to model motion, energy, and other physical phenomena. Then we have integration of exponential and logarithm functions. It is used to integrate function and in modeling, diminishing, returning in production, and the last rule of integration is integration of trigonometric function. It can be used to compute area under curve, especially when the curves are periodic.
Firstly, for our differentiation, we will discussing the mechanical vibration. This application is using second-order differentiation equation. For the setup of the spring system, it showed that the mass is hanging from a spring. Furthermore, the natural length of the spring is represent I, and the hooked object with mass is represent M, and the length of stretched spring is represent X, and also we assume that the equilibrium position is stationary. As shown in the linear model for the spring graph, the spring force is varies linearly with the displacement of the spring from the sketch length. The slope represents the spring constant using the symbol K. Based on the Hooke's law, the spring force F is proportional to displacement x with the spring constant K is giving F is equal to negative Kx, where the negative sign indicated the force opposed the displacement. As we assume the force acting downward is positive, hence the negative spring force is acting upward. Here is the free body diagram with the labeling of every force acting on it, including the gravity force and the spin force.
Next, Newton's law shows that the sum of forces is equal to mass times acceleration. Therefore, we include all the forces we mentioned just now, but acceleration is determined using the second derivative of displacement. Next, the equation is rearranged and is written by mx prime plus kx equals to mg. To make it more complicated, we add linear viscous damping, which is the friction source located here, as shown in this diagram. Based on the graph, force varies linearly with the velocity instead of displacement of the spring. The slope c is the damping coefficient. This force also opposes the motion of force. Therefore, Fc is equal to negative Cv. It can also be equal to negative Cx prime. Now imagine there is a person pulling the mass on the y-axis direction. Additional force applied is vary as a function of time as shown in the updated body diagram. Lastly, the equation includes the friction force and additional force applied, and we can get this equation after we rearrange everything again. The differential equation describes a mechanical system that includes a mass spring damper experiencing gravitational and time-dependent forces, representing a mechanical vibration system.
Now I'm going to talk about integration by using calculation of mass of wire with density. Mass is the integral of the density of the wire times the change in arc length of the curve, which is ds. The equation below is an example of integral of density to find mass. To parameterize the curve C, we express the position of point of curve at parameter t, which is the angle measured from the positive x-axis. As a result, we will get r of t equals cosine t and sine t. After that, we need to differentiate r with respect to t, in which we will get dr over dt equals negative sine t and cosine t.
Next, we calculate the change in arc length ds, which is equal to magnitude of dr over dt times dt. To find the magnitude, we need to square the both value inside and square root the sum of them. After that, we times dt, and we can find square root sine square delta plus cos square delta times dt. Using Pythagorean identities, sine square delta plus cos square delta will become 1, and so we can find ds equals to dt. Now we have determined ds. The density function is given as px, which depends on the position along the curve. Since the arc is in first quadrant, the range of t will be more than 0 and less than pi over 2. So, by substituting the information obtained, we can get the formula shown here, and this equation allows us to calculate the mass based on the density function. To summarize, by parametrizing the curve, computing ds and integrating the density function over the arc, we can calculate the total mass of a wire along the arc of a circle. Thank you.